Welcome to the penultimate video on Chapter 7 of your Year 2 Applied textbooks. Here we're moving from statics over to dynamics. So when we get to these questions, that means the forces are no longer in equilibrium and we have an acceleration. So if we look at example 9 first of all, what we have here is a particle is held at rest on a rough horizontal plane, which is inclined to the horizontal at an angle alpha, where tan alpha is given as 3/4. So again, as we've said before, we've got one of our Pythagorean triples. So if tan alpha is 3/4, we know that cos alpha, when we need it, is 4/5, and sine alpha is 3/5. Just another way of telling the angle. Obviously, you can use your calculators as well. Now, what we have, the coefficient of friction between the particle and the plane is 0.5. So we're given that mu is 0.5. And the particle is released and slides down the plane. So we are going to have an acceleration down the plane. So as all with these questions, we need to start with our force diagram. So we have a reaction force at right angles to the contact to the surface. Our weight in this question, we're not told the mass, so we'll just call that M. And we are told that the coefficient of friction is 0.5 because it's a rough plane. That's going to try and prevent motion, and the fact that it's moving means that we know the friction force will be at its maximum, so that is going to be mu, which is 0.5 lots of r, and our weight is mg. Now we can put our angle alpha in there ready. So the only difference with these questions, it's very simple. Before we just did two resolving equations at right angles to each other. With these questions you do F equals ma in the direction of motion, and we resolve at right angles to the motion. So you start getting the idea, even though it takes a while to perhaps get warmed up with mechanics. Once you know what you're doing, it's very simple because essentially you're doing the same equations every time. So resultant force is mass times acceleration in the direction of motion, which is parallel to the plane, and then we resolve at right angles to the plane because that's where our forces are still in equilibrium. If it's moving down the plane, it's not moving away or into the plane, so we know the forces at right angles to the motion will be in equilibrium. So we have the component of the weight that's pulling it down in the direction of motion. So we've got mg sine alpha, okay, because it's the part of the force that's opposite the angle that we need, and that's going to be minus 0.5 r is going to equal mass times acceleration. And it's the acceleration we're trying to find. So the only unknown here is going to be r, but if we resolve at right angles to the motion, we have that r is going to equal mg, and the component of the weight adjacent to the angle is cos alpha. So we have r is going to equal 4/5 because cos alpha is 4/5. So r is going to equal 4/5 mg. We can substitute into there. So we have the mg sine alpha, which is 3/5 minus a half of 4/5 mg, which is our value for r being substituted into that equation as well, is going to equal ma. Our masses all cancel out, so we're left with 3/5 of g minus 4/10 of g equals a, and we end up with an answer of a equaling 0.2 g, which is going to be a value of 2.0 meters per second squared to two significant figures. Now for part B, as soon as it starts saying distance, that's when we then go to our kinematics equations. So for part B, we have that it starts from rest, so u equals 0. We have A, we now know, is 2.0 meters per second squared. We're trying to find out S. We don't know T. Sorry, we do know T because it says that T equals 2 seconds, the distance it slides in the first 2 seconds. I was a bit concerned there, thinking we had two unknowns. And V is what we don't know, the final velocity, but we're not asked to find that either. So if I just move up slightly there, you can see those values. So U is 0, A is 2, S is the thing we're trying to find out, the distance it slides down in the first 2 seconds. So we can use our equation S equals UT plus a half AT squared. So if we substitute those values in, we've got 0 plus a half of A which is 2 times by 2 squared, and we can see that it travels a distance of 3.9 meters in the first 2 seconds, keeping the value of A and substituting the exact value into there so that we round accurately at the end. Moving on to example 10 now. This is the one where we have a mass of 2 kilograms here is pushed up a rough plane by a horizontal force of magnitude 25 newtons. So this is quite a common exam style question. It tests because this horizontal force is going to provide a component in the direction of motion as well as to right angles to the motion. So we have to remember to resolve that force into 2 components as well, which is the common mistake students make. They just include it here and forget that there's also a component at right angles to the motion too. So here is pushed up a rough plane by a horizontal force of magnitude 25 newtons. The plane is inclined at an angle of 10 degrees to the horizontal, and given that the coefficient of friction between the box and the plane is 0.3, find the acceleration of the box. So again, it's going up the plane, so our acceleration is in that direction. We are going to, if I do the rest of the forces, we have a reaction force there. We can say straight away the friction force is at its maximum, and the coefficient of friction was given as 0.3, so that's going to be 0.3 R, and we have a weight of 2g. And remember that our angle 10 degrees is tucked in there. So, as we had before, it's the same 2 equations, it's just the fact we've got this horizontal force to consider in addition to what we had in the previous example. So again, F equals ma in the direction of motion. So the resultant force in that direction is 25. And again, if I just put the angle in there, because obviously the angles are corresponding, we're going to have 25 cos of 10 degrees minus 0.3 R, and then minus the component of the weight, which is 2g sine 10 degrees, and that is going to equal mass times acceleration. So 25 cos 10, because it's adjacent to the angle, minus 0.3 R, the whole force, minus 2g sine 10 degrees. That's the resultant force in the direction of motion. That's going to equal mass times acceleration. And then once again, if we resolve at right angles to the motion, because again the forces there are in equilibrium, so we have that R is going to equal 2g cos 10 degrees, and that's the common mistake students make. They just get so used to doing that, they forget about the component of the 25 newtons. So that's plus 25 sine 10 degrees. So if we work out the value of R, first of all, there, we have 2 lots of g, remembering that we take g to be 9.8 times by the cos of 10 degrees. And then if we add 25 multiplied by the sine of 10 degrees, we have that value of R as 23.64 newtons. So if we put that in at the top there, we therefore have 25 cos 10 degrees minus 0.3 lots of 23.64 newtons, I should say, minus 2g times the sine of 10 degrees. And if we divide all of that by 2, we then get our value for A. So we're going to have 25 times the cos of 10 degrees minus 0.3 multiplied by our exact answer for R, and then minus 2 lots of 9.8 times the sine of 10 degrees. And then if we divide all of that by 2, we end up with our acceleration equaling 7.06 or 7.1 meters per second squared. So that's all you need for exercise 7E. In fact, many of you should find this a little bit easier than the previous exercise, as we haven't got the moments questions and things tied into resolving as we had in the statics questions with ladders in 7D. So good luck with that, and then join us for the final video of chapter 7, where we start looking at connected particles.